Hey guys, welcome back to Day 12 Quantum Mechanics. 1926, Schrodinger, right? Inspired by de Broglie's assertion that small particles, like electrons and other ones, should have wave-like characteristics or exhibit wave behavior, he wrote an equation that treated the electron as a standing wave in 3 dimensions. Well, what is that? That equation is H psi equals E psi, and then that's pretty much where we're going to leave it because it gets a little bit more crazy from there. All right, so first of all, psi, that is the wave function. It describes the wave-like characteristics of the electron. Right? So psi is on both sides of the equation. E, as you probably guessed, would be the energy. Right? E is the actual energy of the electron. E. Energy of the electron. What is H? So H is the Hamiltonian operator. It's a set of equations that represents the total energy right? That's kinetic energy and potential energy of the electron in the atom. All right? And so what's an operator? All right? An operator transforms, so on a side note, operators transform one equation into, let's spell correctly, another. Right? So for example, d over dx of x squared equals 2x. So some of you know that, some of you don't. If you've taken like Calc 1-ish, maybe late pre-calculus or Calc 1, you've done derivatives, right? And so 2x is the rate of change of x squared. It's the derivative, right? And so the operator, taking the derivative, is actually an operator, okay? And when you solve h psi equals e psi, you get these quantum numbers. We mentioned them last time, right? There's 3 quantum numbers we get, all right? So let's go out of it, all right? Go down and then we'll go this, right? And so solve the allowed energy levels to get 3 quantum numbers. Right? And this is just for your information. So each energy level is described by a wave function. The system's quantized. Only certain energies are allowed. Wave function is like y equals sine x. And so the standing wave there's the wave function for the lowest energy level for a hydrogen atom. Right? Now, the fixed paths described by Bohr are called orbits. And so we have these things called orbitals that we'll talk about. It's the region of space where an electron is in a particular energy level is likely to be. We care about this guy right here, psi squared. All right? And that's where the probability of finding the electron is. So when we talk about numbers from an equation, right? When we talk about variables, all right? I want to dive into this real quick because a lot of times we get, what does this mean? What does that mean? All right? When we talk about variables from an equation, I did that to you guys, most of you guys would automatically know that's a month, day, year, right? And there are allowed values for these month, day, and year, right? So we had some equations for them every month, right? If, right, the month was 1, then the day values could be what? Well, could the day be 0? No, it doesn't work. Can the day be -5? Nah, that doesn't work. Right? The day can be 1 all the way to 31. Right? Okay? And we really don't have years that are negative here. So usually the years, right, they'd go from 0 on up, right? We have BC, but we don't usually talk, like, I've not seen historians do that. Maybe they do. I don't know. I'm not a historian. If the month is 02, our days are, not 2, sorry, our days are 1 to 28 with an asterisk, because depending on the year here, we could go to 29. If our month was 03, we go 1 to 31. Month is 4, it can be 1 to 30. And you guys kind of get this, right? And so, and you know what these are. So if month is 4, you know that's the month of April. If the month is 8, you know it's August. The month is 12, you know it's December, right? Okay. Now you might not know based on like what year and what day. Oh, that's a Thursday, right? You could look it up. All right, with the calendar, you could definitely look it up. If I give you, 2005 and 4/30, 2005, you could figure out what day of the week that was, right? With the calendar, right? Not right. That's not like, oh wow, that's too hard to do. No, that's actually not that hard to do, right? You just need the calendar, right? And so those are an example of variables with allowed values, and those values depend on the other variables, right? So I can't, if my month is 4, I cannot have a day value of 35. It just doesn't work, right? There is none of that. And so when we solve these quantum mechanics, right, these quantum numbers, right, there are certain values that you get and certain representations, and they mean something, and because of what those are, right, it limits what the other quantum numbers can be. Just like, if the month is 2, you're not going to have day 30. So what are these quantum numbers? The first one, n, which is the principal quantum number, and it's your pal for whatever reason, right? The value is allowed. It's 1, 2, 3, 4, continuing on, and that's the energy level. All right, that's the energy. The next one, we'll use the symbol of L, and that's the secondary quantum number. And their value, it starts at 0, 1, 2, 3, all the way to whatever n minus 1 is. All right, so there you go. There's our allowed value. So if n is 1, L can only be 0. There's only one option. If n is 2, L can be 0 or 1. If n is 3, L can be 0, 1, or 2. And so there are options, right? And that significance, that's the shape of the wave function, or the shape of the orbital. Think of the shape of the orbital. And then there's the third quantum number, m sub L, which would be our magnetic quantum number. And this one goes from -L to positive L. And this is our orbital orientation, right, in 3 dimensions. So those are the 3 quantum numbers that come out of the wave function. Now, you're looking at the screen, you say, oh, there's a 4th quantum number. There is. And this one's weird. It's the electron spin. Some of these quantum objects have spin, right? Most things have spin, these quantum objects. And electrons have a spin of 1/2. All right. And it's a property of the electron. And just like photons, light has a spin. And that spin, I believe, is 1. And quantum number spin of 1, you can actually have more than one in the same space. That's why you can get things brighter. That's why you can have more light in the same space. Electrons cannot be more than one in the same space because it spins 1/2. All right. And that's very important. So it's down here, m sub s, and it's our spin. And so m of s can be plus or minus 1/2. And it's the spin of the electron. So what does it mean? It's a property of the electron. That means it's not coming out of the Schrodinger equation. This is an inherent property of the electron itself. Okay? Now, in effect, it doubles, we call the degeneracy of each energy level. Which means that we can put 2 electrons into each orbital. Not just one. All right. So it's a non-classical property. That means that it's not like not a macroscopic thing. This only happens for the microscopic quantum objects, right? But you can think of it think of it or the electron as spinning one way or the other. All right, and so that would be the spin of the electron. So those are the 4 solutions that we're going to get out of the Schrodinger equation that we care about. All right. And so when we talk about orbitals, what are the orbitals? Well, n can be 1. All right. Now, just like before, when we had the secondary, if you look at the secondary, this is kind of important. All right. When we had the months, month 1, well, that's January. Month 2, February. Month 3, March. Month 4, April, right? We know that. That's not a surprise, right? So you know, if you look at month number 9, oh, I know what that month is. That's September, right? That's not like it's a surprise. So here, for the secondary, if L is 0, it's an s orbital. If L is 1, it's a p orbital. If L is 2, it's a d orbital, and L is 3, f orbital. And there's more, but those are the only 4 we're going to worry about in Chem 1. Okay? So when we n equals 1, the only options for L is 0, right? Which is a 1s orbital. Okay? If n equals 2, L can be 0 or L can be 1. All right? And so we'd have the 1s and, I'm sorry, not 1s, we're in 2. We're in 2s, and we got the 2 p's, right? And because when L is 1, right, m sub L can be -1, 0, 1, there's actually 3 2p's. There's 3 p orbitals. When n is 3, L can be 0, L can be 1, L can be 2. All right? And so you'll have 3s, the 3p, and there's 3 3p's. And then the D's. Well, if L is 2, M sub L can be negative 2, negative 1, 0, 1, and 2. There's actually 5 D's. So there's 3D, 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 3D. Right? So now if you look at the number of orbitals here, N is the number of different types of orbitals. Right? And the other thing is N squared is the total number of orbitals within the principal energy level. Right? So if N is 1, 1 squared, I have 1 orbital. 2 squared, 4. I have 4 orbitals. 3 squared, 9. And last one, we'll do N equals 4. That means L can be 0, L can be 1, L can be 2, L can be 3. All right, and so we're in 4. I have 4s, 4p. I have 3 4p's. I have 5 4d's. And then 3, I got negative 3 to positive 3. So that's 7. Right? I have 7 4Fs. 1, 2, 3, 4, 5, 6, 7. That's a lot of orbitals. I have 16 orbitals. And it just keeps going on. Now, 2L plus 1 equals orbital degeneracy. And what does degeneracy mean? So that means they have the same energy. So, for example, it's like if you went to a sporting event or a play or whatever, and all the tickets were the same price. They'd be the same degeneracy in price. Some tickets cost more than others in some of like the sporting events. And so you would go, if you're in this section, probably going to be very similar. Now, maybe the stadium is big enough where the one part of the section is at one price and another part is another price, right? Well, here we're saying that 2L plus 1 is the orbital degeneracy, and that is the number of orbitals in a set. With the same energy. So if L is 1, that means you'd have 3. If L is 2, you'd have 5. If L is 0, you'd have 1. Right? That's just how that works. Now, one thing that we have that happens, which makes this very complicated, very hard to calculate, is that atoms other than hydrogen, right, with more than one electron, get interference between them, right? And so, let's write this down. Atoms other than hydrogen, right? They have more than one electron and get interference. What happens is that we assume orbitals remain the same, but do get called a loss of degeneracy. Right, which means that S or P and D, F orbitals no longer, right, equal in energy. All right, and that'll help us. So what are the orbitals? Let's look at the orbitals. These are the probability of finding an electron in an area around the nucleus. Okay. First one up there is S. S is a sphere. Now S doesn't actually stand for sphere, but S is a sphere. And it's 360 degrees, right? So L is always going to be 0, and M sub L is always going to be 0, because there's just one way to orient the sphere, or infinite ways if you want to do that. So there's just one way. P orbitals. All right, they're like dumbbell, peanuts, whatever you call it. L is 1, so M sub L is -1, 0, 1. And the three p orbitals are a p on the x-axis, a p on the y-axis, and a p on the z-axis. So what happens in three-dimensional, z becomes the vertical axis in all this, right? You have x and y. Now, in this case, x this way, y that way. They rotate them around, depends on the book, the picture, who's writing it, right? A lot of times, z is vertical, x is this way, and y is in and out of the screen. But this way it works just fine. If these are d orbitals, L equals 2, and so M sub L would be -2, -1, 0, 1, 2. And what are they? Dx squared minus y squared, dxy, dyz, dxz, and dz squared. So these are the 5 d orbitals. So look, these three in the middle are basically the same, just rotated. So this d orbital, it looks like almost looks like two of these p orbitals together, right? And this is in the xy plane. This is in the xz plane, and this one is in the xy plane. So they're all 90 degrees from each other. The first one, x squared minus y squared, is on the x and y axes. And the fifth one is, this got this weird donut around it, right? And then it's got, lobes on the top and the bottom on the z-axis. Those are the orbitals that we are going to talk about. Your book may have pictures of f orbitals. If that's the case, that's the case. If not, don't worry about them. We're not going to do anything with them. In fact, most of the time, we're going to be up here. All right, because when we talk about this course and then the next 2 courses, when you get organic, that's where we live most of the time. Now, we want to know how the electrons are placed in here in these atoms, because we want to be able to predict behavior. And so we can bring up what we call the electron configuration. There's 3 principles. There's the off-ball principle, from Bohr, right? That we fill in orbitals in order of increasing energy. Unlike if you go to movie theater, a religious service, class sometimes, whatever it is, you go in there, and a lot of times you don't sit front and center. And I played college football, and the seniors would go up, sit front and center. And if you were not a senior, it didn't matter how good you were, you did not get to sit in front and center. The seniors got to sit in front and center, right? So it's kind of the opposite. It's kind of like how that worked, where you sat up front center to the coach, right? That's what you wanted to be, all right? And then juniors, then sophomores, then freshmen. And you wanted to work your way up, but you could only go up as far as you could, all right? And so that's how these electrons fill. They go front to back instead of like back to front. They go front to back. Closest to the nucleus to further away. The second principle is the Pauli exclusion principle. And that's only 2 electrons in each orbital, one with opposite spins. So by definition, the first one gets a positive spin, the second one gets a second negative spin. The electrons actually can flip their spin, so we just by convention, positive, negative, but electrons only have 2 electron atoms in each orbital only have 2 electrons, and they have opposite spin. And lastly, Hund's rule. And this is maximum multiplicity. As far as possible, we keep the electron spin the same, or parallel, we call it, in degenerate sets. All right, so how we write electron configuration is N, L, number of electrons. And then it goes back to N, L, number of electrons. All right? And with orbital notation, we use boxes to represent orbitals. And we use arrows to represent electrons. And that would be ms plus 1/2, and that represents ms equals minus 1/2. All right, so now we have all the tools to start putting these into electron configurations. All right, and so we're going to start right with hydrogen. So make sure you have your periodic table ready to roll. All right, we're going to go through the first 10. And then we're going to be done with this part, and we'll do more electron configuration practice next. So the first 10, hydrogen. Well, hydrogen is in period 1. So you got period 1. If you look at period